Now that we know how to balance equations, now we can use those balanced equations to undergo and understand the difference between reactants and products and how much of those are going to be used or created during a chemical reaction. So let's look at an example. If we have nitrogen, molecular nitrogen, plus 3 units of molecular hydrogen, that can react to form 2 units of ammonia. So how many moles of molecular nitrogen are used when 2.3 moles of NH3 ammonia are produced? So here we can see this number doesn't match up. We're not getting exactly 2 moles. So how do we set this up? What do we know? That's kind of the first thing. What do we have and what do we know? So we know we have the stoichiometric equivalencies, so we can make some conversion factors. We know that 2 moles of NH3 is equivalent to 1 mole of NH2. That's right, that we don't see that 1 there, but we know that means a 1. It's inferred. What we have is 2.3 moles of NH3. That's what we are given, right? We're using that. That's what's produced. We want to know then how much of the N2 do we start with in this equation. So how do we do this? I typically like to start with what we have or what we're given, and we're given 2.3 moles of NH3. Now we can use this conversion factor to cancel out the NH3 moles. So we know for every 2 moles of NH3, we will have 1 mole of N2. And the moles of NH3 will cancel out. We're left with moles of N2. So we basically take 2.3 and divide it by 2, and that should give us 1.2 moles of N2. So that's a simple problem where we're now utilizing the stoichiometry of a balanced equation. Remember, this has to be balanced or this won't work. We're using those stoichiometries to solve problems, to figure out different types of how much we need to put in or how much we're going to get out of these types of chemical reactions. Here's another example. We're looking at 0.575 moles of carbon dioxide is produced by the combustion of propane, which is C3H8. How many moles of oxygen are consumed in this? And I'm giving you an unbalanced equation. I'll try to, in an exam or a quiz, let you know if it's balanced or not, so you don't get tricked by just assuming it's balanced and then getting the wrong answer. I'll tell you it's unbalanced, so you'll have to balance the equation. So the first step is we need to balance the equation, and then the second step is to identify what stoichiometries we can use in order to make a conversion factor. I like to start balancing these equations by looking at the types of atoms on both sides of the arrow. CHO, CHO is what I have. I have 3 carbons here. I have 8 hydrogens, and I have 2 oxygen. Over here I have just 1 carbon, and I have, so then I have 2 hydrogen, and I have 2 plus 3 oxygen. So how do we fix this? One of the things that we'll have to do is this more complex group, we're going to have to multiply by 3, right, to get this to change into a 3. That also influences the number of oxygens I have. 3 times 2 is 6, plus I have this one over here. So I would have 7 at this point. So we're still not balanced. Now I'm going to have to multiply this group, or I can do the hydrogens. So I'm going to have to multiply something else here. Let's start with this group here. So if we move this to the hydrogen, if we want to get the hydrogen up to the 8 down both sides, we're going to have to multiply by 4 here. So that would be, now we have 8 hydrogens, so this is correct, and this is correct so far. And now we have to update this number. We have 6 plus 4, we have 10. So now we have too many of the oxygens on one side. We can fix that now. We can go back over here and make a 5 there, and that's 10. And now this equation is balanced. Now that I have a balanced equation, I can use this information. I like to, again, start with what I have. I have 0.575 moles of CO2, and here's that CO2 group. I need to make a conversion factor. How many moles of oxygen are consumed? So I'm looking over here and I'm looking at this. This is what I have. So my conversion factor is 3 moles of CO2 is equivalent to 5 moles of O2, right? So I'm using these stoichiometric ratios to create this new equation here. Now I can multiply this by this 0.575 times 5/3. That should give me something close to 0.958 moles of O2. That's what would be how many moles of oxygen are consumed. That would be my final answer here for this one. Now we're going to talk about some different things that might happen during a chemical reaction. And we're going to be talking about something in excess versus the limiting reagents. So here we are looking at a chemical reaction with ethylene and water, and we can make ethanol. This is an industrial process for synthesizing ethyl alcohol or ethanol, which is the same thing. And here you can see we have ethylene, and I don't really love this picture of ethylene. Usually there's a double bond here, but that's not of importance right now. We have C2H4 and H2O react to form C2H5OH. So here is the structure of the ethanol, and here is the water and ethylene. So what happens if the proportions are not met? For example, let's say we have 3 molecules of ethylene and 5 molecules of water. So here's 1, 2, 3 molecules of ethylene and 1, 2, 3, 4, 5 molecules of water. And you'll notice what we have a limiting reagent, which is the ethylene. We don't have enough to completely react with all of the water, and the water is in excess. So these are 2 vocab words that you need to know. It's excess water, and the limiting reagent is the ethylene. So this is limiting us to how much we're able to generate, because we only have 3 of these units that can transform into the ethanol. We don't have any more carbon groups, right, to make these other ethanol functional groups. So that is the most that we can make, because this is limiting us on that ability versus the water that's in excess in this instance. I also want to use this slide to point out the difference between subscripts and those coefficients that go in the front, right? If I have this C2H4 subscripted, that means that these things are all connected to each other. They're one unit that are connected by these little bonds, these carbon hydrogen bonds. They're connected through different interactions with the electrons. So when I have something like, if I would have, for example, 3 molecules of ethylene and 5 molecules of water, right? Those units, that tells us we have these 5 groupings of water. So I can't change the subscript. That changes the whole entire molecule and what it is. So the difference between the coefficient and the subscripts are telling us about the molecular orientation and how it's put together. The coefficients here, the front part, that is telling us how many of those groupings there are. So make sure that you can understand and distinguish between those 2 ideas. So again, in that example, water is an excess reactant. Ethylene is the limiting reactant or reagent. Okay, so now we're going to work on a problem where we explore and identify which one of the limiting reactants we're going to have. So if we have how many grams of nitrogen monoxide can form when 30 grams of ammonia and 40 grams of oxygen react according to the following balanced equation. So we have 4 NH3 plus 5 O2, and that's going to give us 4 NO plus 6 water molecules. I just want to check quick. This is balanced. 4 nitrogen. We have 4 nitrogen. We have 12 hydrogen. We have 6 times 2, 12 hydrogen. And then 10 oxygen, 4 times 1, and then 6 times 1. So that's 6 plus 4 is 10. So it looks like we have a balanced equation. So let's put together our tools. So what do we have? So we know that we have the I want to start with the 30 grams of NH3. And I can now understand how many grams of NO can form so when we have 30 grams and 40 grams of O2. So I want to figure out the grams of NO. And I can do a stoichiometric equivalence with the coefficients that we have here. 30 grams of NH3. The problem is this is in grams, so I need to convert that into moles first. That's the big trick there. And 1 mole of NH3 is going to be equivalent to 17 grams of NH3. How did I get 17 grams? Well, I added a nitrogen, which is about 14, and then 3 hydrogens, which are about 1 each. So 14 plus 3 is 17. So that's how I got that number using the periodic table and my knowledge of the atomic masses for these different elements. Next, now we're going to be able to solve for that, and that gives us about 1.76 moles of NH3. Now that this is in moles, remember I cannot ever do comparative analysis with grams. It always has to be through moles. Now that I have moles, I can use my stoichiometry equivalencies for NH3. I know for every 4 NH3, according to this equation, I will get 4 NO out. And so that is going to give me 1.76 moles of NO. All right, so now I need to figure out, I have 30 grams of NH3 and 40 grams of O2. So let's go through the same process, but now with oxygen. And we're going to do the same thing. We need to convert this from grams to moles. So 1 mole of O2 is equivalent to 32 grams of O2. And I know that because oxygen weighs about 16 grams per mole, and there are 2 of them in that molecule. So I multiplied that by 2 and got 32. So here we get about 1.25 moles of O2, and now I'm going to multiply that by 5 moles of O2 using my stoichiometry here, 5, divided by 4 moles of NO, which comes from this number, and I'm going to multiply that, and I should get about 1.56 moles of NO. Now, this number is smaller than that number, so if I have 40 grams of oxygen, I can only make 1.56 moles of nitrogen monoxide. This is my limiting reagent. And if you remember back in that ethylene problem, we don't have extra oxygen. There's not any more there. So this is the most we can make. And this top one, this ammonia, is in excess. So here we can only make 1.56. We can't make more than there is compound to create. So we have enough oxygen to make 1.56. That's the lowest number that we have calculated. So this is the actual final answer, not the 1.76. We could add more oxygen and make 1.76, but then we would have the opposite problem perhaps, where the ammonia would then be limiting reagent. So, or we could add exactly the amount that we need, and that would be more efficient for our chemical reaction. But that's how you solve this problem. Again, know these vocab terms in terms of excess and versus limiting reagent, because the limiting reagent, the smaller amount, you might get a problem, hint, hint, on a quiz or exam where I'm going to give you 2 different compound amounts from the reactants, and you're going to probably have to run through both of them in order to determine what the limiting reagent is. Now, if you give me this answer, you would get partial credit because you did part of the problem, but you didn't do the full problem to figure out you'd actually get less because you have a limiting reagent there. And this last one I'm going to have you do on your own. I did give you the molecular mass, so the 14 plus 3, right? This is the grams per mole here in blue, and each of these for these molecules or compounds. And so you should use those to solve this problem. If we're looking at 18.1 grams of ammonia is reacted with 90.4 grams of copper oxide. What is the maximum amount of copper metal that can be formed? So this is our we want to go through this reaction. We're going to have ammonia, I give you a number of grams, and copper oxide, I give you a number of grams. Do the same process that I just showed you how to do that. So if you didn't remember, you'll have to go back and look at that. It's the same idea, we're just using different numbers. And you'll make sure that you want to identify the limiting reagent, because that is the reagent that's going to dictate how much we actually get out. So complete this, finish this, and then I'll be walking through. I will make sure that you have this answer correctly. So pause, do this problem, work through it, make sure you understand it before you move on to the next part. Even though we sometimes do our best to get the chemical reactions and the products out, you have probably run enough experiments even already just in chemistry that everything doesn't always go perfectly well, or you're not able to measure things completely perfectly well. So losses occur for multiple different reasons. Maybe some of it sticks to the glassware, or it's hard to scrape off of the glassware. If there are things that have low boiling points, some of it might evaporate. It might stay in solution or be solid and not be completely mixed in to begin with. And then there are also sometimes byproducts or different competing reactions that might occur. You might also have over 100%, which also might seem weird, but you might have contamination, or there might be some moisture, water that was absorbed into your crystals, for example. There are a lot of different ways that you can get over 100% as well. So we're going to talk about reaction yield and how to calculate that. And it's a pretty simple calculation. So we are going to now talk about reaction yield, and sometimes there'll be competing reactions and the formation of byproducts. This actual chemistry that you see here in this video, this is a chemical reaction that has byproducts that actually form, and it takes a certain amount of time for those to form this purple solution. So it's a pretty cool changing color chemical reaction. So the main reaction is this solid phosphorus plus 3 units of chlorine gas, and then we're going to make 2 PCl3. It'll be this liquid, and then we have this competing reaction where we'll make this gas, and then we'll make this byproduct PCl5, and that's a solid, and that's what's actually changing the colors here. So different chemical reactions, it takes some time to build up enough of the product to make the byproduct, which will change the chemical reaction. After these are mixed together, and there's enough time that passes where this PCl3 is formed, then we're able to generate the next chemical reaction where that changes color. So there are 2 different types of yields. One is the theoretical yield. So that's really what we've been calculating so far. So the amount of product that should be obtained if no losses occur and all of the limiting reagent is consumed. So when we're doing these stoichiometry problems, what we are calculating is the theoretical yield. That's theoretically what we should make. And then in the lab, the actual yield is the amount of product that we actually isolate and get in the end. And the calculation is pretty simple. If we want to do percent yield, we would take the actual yield, or what we actually got in the lab, and divide it by the theoretical yield. So that's what we calculated on paper, and multiply that by 100, and that will be our percent yield. So here's an example. If a cookie recipe predicts a yield of 36 cookies and only 24 obtained, what is the percent yield? So we would take this actual yield is 24 and divide it by 36. We take that value, multiply it by 100. So if I go on my calculator, 24 divided by 36, I get about 66.7% yield, probably because someone either ate some of the cookie dough, right? Some of the cookie dough sticky on the spoons and on the other things, or someone ate cookies after they were made. So some of these, this would be 66.7% yield approximately. Okay, so this is a more in-depth problem, and I'm going to have you work through this. If we have 18.1 grams of ammonia and 90.4 grams of copper oxide, you might recognize this reaction. This was the one that we did a few slides ago. The theoretical yield is 72.2 grams of copper. The actual yield is 58.3 grams of copper. What is the percent yield for this chemical reaction? So work through this, solve it. If you have problems, please ask me or your coach for this class, your academic coach for this class, and we will kind of move on and assume that you understand how to do theoretical yields. As a general overview, I just want to point out the biggest thing to recognize here is that we need to really go through, if we want to make comparisons within the lab and on paper kind of ideas, we need to always go through moles. So it's really the only way that stoichiometry works if we're trying to look at one substance, whether it's an atom in a molecule or two different molecules in a chemical reaction. We always have to do that comparison, and we can only create those different ratios, right? Those conversion factors when we have molarity. We cannot do that with grams. So we would need to look at, if we have grams of a substance, we need to convert it to moles using atomic masses or molecular weights to get to moles. Then we can do those comparisons, and then we can figure out the grams or maybe how many of those elements through Avogadro's number, which is another type of conversion factor. So just make sure that when you are doing these conversions, we're not trying to do those in grams. They always have to be in molar units. That concludes chapter 3 content. We're going to come back. We'll still use all of this information and apply it in different ways, but we're going to more look at more chemical reactions in water and different types of chemical reactions, ionic reactions that occur in water, and we'll still use all of these stoichiometries and understanding in those conversions in order to understand the chemical reactions that are happening there. But this is the conclusion of chapter 3 content.